This is Kamran, and I'm going to talk about CPU, memory, and application execution. First of all, let's see who am I and why I chose this topic. My name is Kamran, a software engineer. You can find me on LinkedIn, YouTube, and my blog, sardine.dev. And why did I choose this topic? In short, because the concepts and basics are so important. I was going to talk about C Sharp tips, and I will talk, but not in this video. But something changed my decision. You know, how this topic is related to C Sharp. When I was reviewing C Sharp to create a roadmap for it, I found some fundamental questions about very basic concepts that I knew the typical answers, but I couldn't understand the meaning of them, such as what is concurrency, what is parallelism, and why the array is faster than the list, and what do cancellation token does, and these type of questions. You can write your application without having a deep understanding about what happens in your CPU or memory or about data structures. But if you know about the basic fundamentals, you will learn faster and easier. So I started to research, and what I'm going to present is part of my research result. We are going to talk about CPU, some definitions and understandings about that, about memory, application execution process, about motherboard, some components of CPU and motherboards, about processors, and other related topics. For the sake of simplicity, I picked up the 6502 CPU that was used in computers like Apple II and Commodore 64. That's really old one, but the concept is the same. Okay, CPU. CPU shows four central processing units. It's the brain of the computer. It's executing the instructions, like adding two numbers. Okay, it's running the logic of that instruction. CPU is an executor. It cannot keep the data inside itself. Uh, yes, it can, but that's not what I'm talking about. We will talk about registers inside the CPU later. Anyway, we need somewhere to store the data. It's the memory, right? And what is application? The common definition that, of course, you have heard is set of instructions. That really what I'm writing codes. I have UI, I have libraries, I'm connecting to the databases, and etc. And all these instructions, yes, they are. In fact, when you publish or compile your code, it's converted to the machine code. In C Sharp, it compiles into an IL or intermediate language, but at the end, all applications will be in machine code. And this machine code is nothing but instructions. In fact, the CPU, with all magic that does, is just doing a simple job, and it's running instructions one by one. If you look at the inside of a CPU, you will see particular wire that turns on and off to help keep everything in sync. That wire is called a clock, and in the modern CPUs, they are measured in gigahertz. Giga means billion, and hertz means times per second. So you can imagine how many turn on and off will happen in a second in modern CPUs. You can find these 6502 CPU simulations on visual6502.org. On this website that you can see on my screen, On this website, you can see a simulation of 6502 CPU, and in that simulation, clock wire turns on and off twice per second. As I mentioned, in the modern CPUs, it's happening in gigahertz. We'll get back to the CPU job soon. Let's take a look at what I mean about simulation. Okay, you can see on the screen that is blinking, and this blink means it's keeping sync the CPU. Okay, let's get back to the motherboard. On this slide, you see the CPU and memory on the motherboard, right? As you can see, there are some pins here. There are some pins on the CPU which it's communicating with the other components through these pins. In fact, CPU is sending or receiving the data and instructions through these pins to the motherboard, and motherboard transfers the data through some wires to or from the other component, data buses and the address bus. Okay, before going into the CPU, let me explain a bit about RAM, because we're going to need that. Okay, I'm going to draw the CPU and RAM, and please accept my apology because of my bad drawing expertise. I'm not Bob Ross. Okay, we'll get back to the CPU later, but let's see what is a RAM. It's random access memory, and you can consider RAM as a sequential blocks that each block has an address and it contains piece of data. As I mentioned, CPU needs data to calculate or instruction to execute. That data is stored on these blocks. Normally, CPU requests and process each piece of the data from the RAM, one after another. However, you can command the CPU to pull the data out of order, and that is why it's called random access memory. Okay, let's quickly see what happens when we want to run a program. The CPU sends the address of the first block to the RAM to retrieve the data. The RAM address is ones and zeros, like 0, 0, 0, 1, 0, 1, something like this, 2, 4, and 6. And when CPU wants to get the data of an address, it turns the address bus wires on and off to represent the 1 and zeros. RAM will find out that, you want the data of this address, but won't do anything with that address until CPU turns the set or enable wire. I mean, there's another wire, another two wires, which first is enable, or another one is set. The enable means that, hey, I don't need to write anything. I just need the data. And set means that, hey, I want to write something in this address. In our example, the CPU wants to read the data and turns the enable wire on. The RAM automatically sends back the data to the CPU through the data bus. This is the data bus, and this one is address bus. After processing that piece of data, CPU sends another address to the RAM and turns the enable wire and gets another data to process. This process, these steps happens over and over again inside the computer. And if CPU needs to store some data, it will send the address of RAM and sends the data through the data bus and turns the set wire on, then memory will store that data on that particular address. The data could be instruction, numbers, characters, or addresses. I mean, you can store the number, maybe, or another instruction, or maybe character, or even some addresses to the input and output ports, like your keyboard, mouse, monitor, and anything. These instructions could be load, that loads the data of an address of RAM, or it could be add two numbers, or jump and jump if to break the order of reading data and read the data of unordered blocks of RAM. Also, there are in and out instructions to get the data from input or send it to the out. Now let's see what are CPU components. I mean, inside the CPU, we have some components. You can find components such as ALU, or arithmetic logic unit, which does the mathematical operations, CU, or control unit, which decodes the instructions and sends command to the ALU or other components. There are really tiny memories that we call them registers, and they keep temporary data. I will explain about these components a few minutes later. We want to review all this information with an example, and the example is, suppose that we have an application for guessing numbers. And I mean, let's suppose that we have hard-coded a number like 9, 10, or something, and we're getting inputs from the user to check whether the input is equal to that number, like 9, or not. If it is equal, we will print the you guessed right, or something like this on the screen. And if that's not, we print the wrong guess. But before that, let me talk a bit about the process and threads and what's the differences of them. Imagine we wrote our application and compiled it. Now we have an installed application on the hard drive, right? And when you run, like for example, we have Facebook application, or even our application that I explained about that. And when you try to run the application, the operation system, it converts that application to a process. I mean, when you double click on your application, it converts to a process. Let me draw like this, and this is a process. A process is basically a program in execution. We write our computer programs in a text file, and when we execute this program, it becomes a process that performs all the tasks mentioned in the program. Process is a running application, and OS will load the application on the RAM. Remember application definition, set of instructions, right? Exactly. Now the OS puts the set of instructions on the RAM. And why RAM? I mean, why couldn't save or use from the hard drive? Why the CPU is not reading the application from hard drive? Because of speed. Reading the data from hard drive is really slower than reading it from the RAM. Have you noticed the loading bar, process bar, or progress bar when you are really loading an application? It means that your application or part of it is loading into the RAM to have a better speed. Otherwise, you would see lags and delays when you play a game. Anyway, now we have a process, right? And I mentioned a set of instructions, right? Okay, now what is a thread? Thread is a smaller sequence of instructions that can be managed independently by a scheduler. A thread is also a set of instructions that is ready to be executed. Each application at least has a thread, one thread called main thread, and some applications have multiple threads. In our example, we don't need multiple threads. All instructions can be run in a single thread. In the beginning, each CPU could run only one thread. I mean, years ago, at that time, each CPU could run only one thread. And if you had multiple applications or threads, you needed to wait until the first thread was finished. And then the OS would send the next thread to the CPU. It means if you would like to run Instagram and Facebook, you would need to wait until the Instagram to be closed. Then you could run the Facebook. It's painful, isn't it? But how about adding multiple CPUs to the computer? I mean, having 4 CPUs on the same computer. That was a solution, but it could be better by putting multiple CPU cores into one CPU for some performance and cost efficiency. How about making the CPU core to run 2 threads? I mean, why a core should only run one thread at the same time? Awesome, right? I mean, if we could do that, but still we could only run 8 threads on a 4-core CPU. I mean, each core could run 2 threads at the same time. We have a bunch of processes running on a computer. I mean, if you check on your computer, you could see many processes that they are running at the same time. But how is it possible? I mean, a CPU can only run one thread. Let's see, like this is a thread of a process. It has some instructions like instruction 1, 2, 3, and 4. And each CPU or each core of CPU could run only one thread, okay? But in your computer, you could see many threads or many processes that are running, right? And how is it possible? Okay, it's time to know the scheduling algorithm. We have multiple threads that are ready to be executed. But on the other hand, we have only 8 processors on our computer CPU to run them. And the OS has some algorithms to run more than 8 threads at the same time. I mean, that's not really same time, but let's see what is that. The first algorithm, it's FIFO. I'm going to name some algorithms. It's FIFO. I mean, first in, first out. It means that the first thread that comes, or first task, is the that comes into the CPU. It's the first one that is going to be executed. And another one is shortest job first. I mean, at the FIFO, what happens if we have a really long thread? That time we will have only one process running. And for example, how about having multiple short tasks or small tasks, small threads that they could run only a really short time? Isn't it better to run them first? Okay, another algorithm is shortest job first. It means that always do the task that has the shortest remaining amount of work to do. That's not bad, but it has some problems. For example, what will happen if we had many short jobs and one long process or thread to execute? Never will run the long thread, right? Another one is round robin. It means that each task gets resources for a fixed period of time, and this one is better, more better. And there are other algorithms that I'm not going to talk about them, just they're just introduction. Okay, the important point is when the cores are executing our threads, it means that we have real parallelism, and all 8 threads are running at the same time. But when we are using, for instance, the round robin algorithm, in fact, the CPU is not running them at the same time. Instead of that, it's assigning the CPU to each thread for a short and defined time. and sends, for example, the thread for 20 milliseconds to the CPU, and then saves the last executed instruction somewhere, and then sends another thread to be executed for next 20 milliseconds. You see, they're not running parallel. I mean, but because of the CPU speed, you think they are running at the same time. And on the UI, you see all applications are running together, but in fact, they're not running at the same time. The computer or your OS is switching between your application, but because of the speed, you cannot see the delay time or the switch time. Now let's get back to our example, guessing numbers, but let me clear the screen and draw again. Okay. Do you remember our example or sample application? It was about guessing numbers, right? We had some a number, hard-coded number on our application like 9, which we were requesting user to input a number, and then we could compare the two numbers to check whether they are equals or not. Okay, when the CPU wants to run our application, it sends the address of the first instruction to the RAM, right? And we had the address bus, which the CPU sends the address of the first location of our application or our first instruction to the RAM, and then turns the enable wire, like that was enable, and this one is the set wire. It turns the enable wire on to tell to the RAM that, hey, I need just the data of this location. I don't want to write something. I just need the data. And the RAM sends back the data, which is like a load instruction. Okay. Load, maybe false or something. Well, let's just, for simplicity, let's have the load instruction. And this is the address 0, 1, 2, 3, 4, and so on. Okay. For example, let's see, let's say it's load 1. Okay. And the 9 is here. And the RAM will send back to the CPU the load instructions through the data bus, right? Then CPU processes the load instructions, which contains the address of the data that needs to be loaded, right? This is the one. This is not the data. It's the address of the data that needed to be loaded. And CPU requests the next data, which is in instructions, and the address of input, which is keyboard in our example. For example, this is in, and the address of our input, like keyboard. The next instruction is compare, okay? And ALU compares, we had an ALU component on our computer, right? ALU compares the 9 and the given number, like, for example, let's say it was 3 or something, okay? The next instruction would be jump if, and this is jump if instruction, right? Which follows with an address to jump to that address if the number and 9 are equal. I mean, this number that we inputted through the keyboard and 9, they're equals. And if they are not equal, it will ignore the jump if address and goes on, which is printing like something WRONG, that prints wrong word on the screen, right? Then it will process the next instruction, which is jumping to the in instructions. I mean, it's the next command is writing character W and RONG, and at the end it will jump back to the this block, this instructions, and do the same steps again and again to find or get the correct answer. And then it the 9, the user answer is 9. It will run this command, jump if command or instructions, which it goes to another location of the memory, which is commanding to print out something like maybe you guessed wrong, like guessed right. Okay, and maybe something else. And you see, this is really simple, but as you know, computer is doing really magic. It's doing great. It's running or executing really complicated applications. I don't know, maybe Office, your movie, your games, and that's really amazing that after all of that huge or large applications, they're just simple instructions, simple numbers, and even it's going to be better if you know that there is no load instruction. There's no L, there's no O or something like 9. It's only 0, 0, 0, 1, 0, 0, something like this. It's just 0 and 1. And why it's like this? And let me give you a quick introduction. You remember about the data bus and address bus computer or our components. There are some wires which each one is representing 0 or 1. And 0, it means that it's turned off, and if it's 1, it means that it's turned on. And by this instruction, we are telling to the RAM that, hey, this is the address. This is the address of the data that I need to load that one. And also for the data, that's the same. There are some wires that if it's 1, it means that it's turned on, and if it's 0, it means that it's turned off. Yes, it's turned off. And we have some default values, right? In our programs, like for integer, we have 0. For Boolean, we have false. And why these default values are kind of like 0, false, and for double and other numerical types, they are 0, because of saving energy. Why? Because, as I mentioned, if it's 0, it means that it's off. It's no voltage or something like that. Okay. There's no energy. There's no lights on. Let me make it simple. There's no lights on. Okay. It's just wires that they all are turned off, right? So in 0, it means that we have less energy to spend. And also in Boolean, it's 0, in fact, right? It's again some wires that they are turned off, some lights that they are turned off. And in the memory, in the old types of memory, they're storing like this, and that means that there's no much energy to spend.